So in this video, we're going to be looking at calculating something called Gibbs Free Energy. Now, starting off, we can actually predict whether a reaction is going to be feasible or not, whether it's going to be spontaneous or not. In other words, will it actually happen by calculating the Gibbs Free Energy. If we have a Gibbs Free Energy, delta G value that is negative, that's going to be less than 0, then we say the reaction is going to be feasible at that temperature. But then, of course, if delta G is going to be positive, where it's above 0, then we say that the reaction is not going to be feasible at that temperature. Now, of course, to calculate Gibbs Free Energy, where you've got the units of kilojoules per mole, you know that you can take the enthalpy change itself, which is also in kilojoules per mole, and you can subtract the temperature in Kelvin, and then, of course, times that temperature by the change in entropy, which you need to convert to kilojoules per mole as well. So in that case, you'd end up with kilojoules per Kelvin per mole for entropy change itself. So yeah, in terms of that, then you can get a value for delta G, and of course, if it's going to be negative, if it's going to be 0 and below, you actually end up with the reaction being feasible, meaning it can actually happen at that temperature. Whereas if it's positive, it can't really happen. Now, with this equation of delta G over here that we need to remember, of course, we can actually rearrange this to find a temperature in which the reaction actually becomes feasible. In other words, where delta G is equal to 0. And what you can actually do is, of course, take delta G, make it equal 0, and then that's going to be equal to delta H minus T delta S itself. And then, of course, you'd rearrange this by taking the T delta S term, plus it on either side, so you end up with T delta S is equal to delta H. And then, of course, you would rearrange it by dividing by delta S on either side, and you end up with the following equation over here. Now, a common mistake a lot of students make is they actually remember the wrong equation. So just assume that delta G is going to be equal to 0 when asked these questions, and then you can actually calculate a value for temperature. But just remember that temperature is going to be in Kelvin itself, because you're looking at temperature as a scientific unit. You do need to be able to convert to and from degrees Celsius with this, just like an ideal gas. So yeah, moving on, let's try an example. We've got here a reaction, and we've got the thermal decomposition of zinc carbonate. We're asked if it's feasible or not at 450 Kelvin. So we've got our temperature there. We've got our delta H value here, which is going to be an endothermic reaction. And then we're also given some standard entropy values, which of course we can use to find the entropy change. Now, to find the entropy change, just as before, what we would do is, of course, we would take our products. Remember, you've got SPAR, products minus reactants. You're going to take your products, which in this case is going to be carbon dioxide and zinc oxide, one lot of each one. So that would be, of course, I've got 214, and then I've got that added to 44. And then I'm going to subtract my actual reactants, which in this case is zinc carbonate, and that's just going to be a value of 82. Now, of course, I put that in my calculator, I end up with 176, and that's going to be joules per Kelvin per moles itself, right? Now, of course, we're trying to calculate delta G, and normally we do that in kilojoules per mole, so I do need to convert this, so I know that my entropy change is going to be equal to, and then it's going to be 176 divided by 1000, and we end up with, of course, 0.176 itself. And then in this case it's going to be kilojoules, and then it's going to be per Kelvin, and then it's going to be per mole as well. So yeah, there's my first mark there in this exam question. What about the next part? Well, I need to calculate a value for delta G, and I always state the equation in this just because in some cases you can actually get some marks. So delta G is equal to, and then it's going to be delta H minus, and then it's going to be T delta S itself. So of course, I've got my enthalpy change value, which is given to me, and we're told it's going to be 71. And then I'm going to subtract the next bit, I'm going to put in brackets, my temperature, which is 450 Kelvin, times by my delta S value that I calculated earlier as being 0.176 itself. I put that in my calculator, and what I end up with is a value that is going to be minus 8.2 itself. So we know, of course, we've got a value for delta G as being a negative number. It's going to be minus 8.2 kilojoules per mole. So we know that the reaction is going to be feasible. So what do we normally say at the end of these questions? Well, it's asked us if it's feasible or not, and we need to show this by calculation. Well, we know that, of course, delta G is going to be less than 0. So the reaction is feasible at this temperature of 450 Kelvin itself. And of course, there's our final mark there. Now, of course, there's 3 marks over here so far. Just remember, you could be asked to find the temperature at which delta G is going to be equal to 0. In other words, when it becomes feasible or when the reaction can actually happen, when it's spontaneous itself. So yeah, have a go at the following question over here. Pause the video, and once you're ready to move on, resume and we'll go over it together. So yeah, here we're asked to calculate the minimum temperature in degrees Celsius at which the reaction becomes feasible. So we know delta G, that must be equal to or less than 0 itself. Now, of course, we've been given a delta H here just like before, and we've got some values to calculate the entropy change itself. Now, of course, just like before, I'm going to work out a value for entropy change very quickly. So I've got delta S, and that's going to be equal to my products minus my reactants. Remember, SPA, 44, add 214, and then, of course, I'm going to subtract a value of 82 for my reactants, and I end up with 176, and that's going to be joules per Kelvin per moles itself. But of course, we want entropy change to be in kilojoules per Kelvin per mole, and of course that would be me dividing that number by 1000. So 176 divided by 1000, that gives me 0.176, and that's going to be kilojoules per Kelvin per mole. And then there's my first part there done. Now the next part, you need to be able to rearrange this again. So remember, when delta G is equal to 0 or most 0, you know the reaction becomes feasible at that temperature, and you rearrange to find temperature. So let's say delta G is equal to 0, that's going to be equal to delta H minus, and then it's going to be T delta S. To rearrange that, I'm going to add T delta S to either side, so I end up with T delta S being equal to, and then it's going to be delta H itself, and then I'm going to divide both sides by delta S, so I end up with temperature being equal to delta H divided by delta S itself. Now I've got my values, which in this case we know it's going to be, of course, for my enthalpy change, 71, and I'm going to divide by 0.176 itself. I'll put that in my calculator, and what you end up with is a value of 403.4 Kelvin, which of course is going to be our temperature in Kelvin, but we want to find our temperature in degrees Celsius. So we know it's just going to be 403.4, subtract 273 to turn it into degrees Celsius, and that gives us a value of 130.4 degrees Celsius itself. I'm just going to go with 130 degrees Celsius just to give it to 3 significant figures, because that's normally what we go with in our OCR exam board. So yeah, moving on, feel free to pause the video and have a go at the following question. So yeah, in this case, we've got some entropy values given to us where we can see we've got our reactants and products there. Remember, to calculate entropy change, it's just products minus reactants, SPA. Now, we're told here that a chemist proposed producing methanol at 525 Kelvin using the reaction below. We've been given our enthalpy change over here, which we can see is exothermic, and we're asked to predict with a calculation whether the production of methanol is going to be feasible at this temperature itself, right? So yeah, of course, as normal, we would find our standard entropy change, which we know is going to be equal to our products minus our reactants. So we've got 238, and that's going to be subtracting the rest of it. I'm going to put it in some big brackets because we're dealing with more than 1 mole of hydrogen. We've got 131 times by 2, because we've got 2 lots of it, and that's going to be added to 198 itself, because I've got 1 lot of carbon monoxide. So yeah, I've done all my products, I've done all my reactants as well. I'm just going to type that in my calculator, and I end up with a value of -222, and that's going to be, of course, in joules per Kelvin per moles itself, but of course I want it in kilojoules, so in that case I'm going to take -222, divide by 1000, and I end up with -0.222, and that's going to be kilojoules per Kelvin per moles itself, right? So yeah, there's my first mark there. The next thing is of course I've been given delta H, but just be aware you could be asked to calculate delta H by using combustion data, Q equals MC delta T, lots of different ways to calculate delta H, but in this case we're going with this. And yeah, to find delta G, I know that I'm going to do delta H minus T delta S, and then I'm going to have, of course, my delta H, which is going to be minus 91, and I'm going to subtract my temperature of 525, it's already in Kelvin, times by my entropy, which is going to be minus 0.222 for the entropy change. I put that in my calculator and I end up with 116 itself, and that's going to be, of course, in kilojoules per mole. Now, of course, we can see that this number is going to be positive. Now, if delta G is going to be greater than 0, we know that the reaction is not going to be feasible at 525 Kelvin. So yeah, moving on then, if you were to look at the next question, feel free to pause the video and have a go at this slightly more challenging question where you've got to work backwards. So you're looking at this question, we're told carbon disulfide, it reacts with dinitrogen oxide as shown below. We can see we've got an equation over here, and we're told the free energy change this time, delta G, is going to be minus 2672 itself. So we've been given our value for delta G, we've been given a temperature as well, which of course we know that's going to be 298 Kelvin, because of course we need it in Kelvin, the temperature. We're asked to use the standard entropies here, and we're asked to calculate the enthalpy change, delta H, of the reaction itself in kilojoules per mole. So of course what we're going to have to do here is because we're trying to find delta H, we're going to need to work out delta S. We know delta G, we've worked out kind of our temperature, to be honest, and we can actually rearrange to find that delta H value itself. So now the first thing is I'm going to try and find a value for my entropy change. So I know I've got 8 lots of nitrogen, so I'm going to use some big brackets here because it's going to get quite complicated. I've got 8 times by 192 itself, and that's going to be added to my value of 214, but of course I've got 4 lots of 214, and then of course I'm going to add a value for sulfur, which is 256, and there is my actual products done. Yeah, so I've done these 2 values as well as nitrogen there so far. Now of course I've got 8 lots of dinitrogen oxide, so in that case I've got N2O, 8 lots of it, so that's 8 times by 220, and then I've got 4 lots of carbon disulfide itself as well, so I'm going to have 4 times by 151. Of course I put that in my calculator and I end up with a value of positive 284, and that's going to be in joules per Kelvin per moles itself. Now of course the next thing is I need to find delta S in terms of kilojoules per Kelvin per mole. So in that case I take 284, divide by 1000, and I end up with 0.284, which is a positive number, kilojoules per Kelvin per mole itself. So yeah, there's my first part done. Now of course we're given a value for delta G itself, which we know of course our equation is going to be delta G is equal to, and then it's going to be of course delta H minus T delta S, but then I know my value for delta G, so we've got minus 2672, and that's going to be equal to a value of X for delta H, or I'm just going to put delta H in this case, subtracting my temperature, which is 298 times by, and then it's going to be delta S, which is going to be 0.284 itself. Now of course if I were to simplify this down, I've got minus 2672 is equal to, and then it's going to be delta H minus, and then it's going to be 84.632 itself. Now of course to get delta H on its own, what I'm going to do is I'm going to add 84.632 on either side. So delta H is going to be equal to minus 2587, and it's going to be kilojoules per moles itself. Now of course I get a mark for the answer here, and then I get a mark for actually using 298 as a temperature in this case, so 3 marks in total.